in a way, I want to define what I mean by growth stress. Actually, what I refer to by growth stress here, and most people do, is the measurement of a stress that develops in the oxide at temperature, at the oxidation temperature. And it comes about from a number of different reasons that you're well aware of, things like defect in ion transport properties, the atomic structure, the microstructure, and then, of course, the deformation and relaxation modes that this leads to. And I'm just showing as an example a paper by Evans and Cannon from a number of years ago, showing how the microstructure can directly influence the appearance of a growth stress. And this is truly a growth stress in that it arises from the additional the addition of further oxide into the oxide scale. But the other point I want to make is that growth stress isn't necessarily constant with oxidation time. For example, in some cases, it's not really a growth stress, it's a transformation stress, such as when you have a spinel that converts to alpha alumina, as we shall see in the work I will present, or if you have the classic transformation from a transitory alumina on nickel aluminide to alpha alumina. These in and of themselves displace atoms, causes strains, which leads to the appearance of a stress in the film, but they're not really growth stresses. They arise from the growth of an oxide film, but then manifest themselves when they are converted to the other structure. And then, of course, microstructure can change with time. And if the growth stress depends on the microstructure, as I showed in the example above, then your growth stress, the rate of growth stress increase will not be constant with time. Continuing in this vein, besides growth stresses, of course, there's the thermostress that we are all familiar with, and that comes about directly from the CTE mismatch between the metal and the oxide. And it depends, of course, on the delta T that one is working with, and then the difference in the coefficient of thermal expansion between the metal and the oxide. And of course, on cooling, this normally is very high compressive stress because of the differences in these coefficients. Now, the other point I want to make up front, and it will come back to several times during this presentation, is that often simultaneously you have stress generation and relaxation. They don't necessarily occur independent of each other, and that the relaxation mechanisms can operate both in the oxide and in the metal when the stresses are sufficiently high. And because of this, it's not in many cases a very straightforward type of phenomenon, because there are competing processes and many processes going over at the same time. And that's why it's so important to be able to model these and to get data that can help develop models to differentiate between the different processes that are contributing to the appearance of these stresses. So very quickly, we use synchrotron radiation at the Advanced Photon Source at Oregon National Laboratory to look at stresses in thin oxides forming at temperature on various alloys. In this case, it's all alloys that formed alumina. And so we're strictly talking about stresses in alumina oxide scales. This was done by at low incidence to concentrate on what's going on in the oxide as opposed to the metal. And because we're using a high brilliance source, we typically can detect alumina from its earliest stages of growth. We're usually within 2 minutes of getting to the oxidation temperature. The way we did this is by a well-known technique in the diffraction community called sine square psi analysis, and which means we measured the 2 theta position of a particular alumina, alpha alumina HKL line at 5 different tilt angles, and repeated this every 5 to 14 minutes for up to for usually around 4 hours, but anywhere from 2 to 12. So if you look at one particular 5 tilt scan shown by the encircled line, we then get 5 different d-spacings from the 2 theta measurements, and the d-spacing versus the sine square phi gives us the stress that we've measured from the slope of that line. And it's very insensitive to the initial d-spacing. We don't have to know the stress-free d-spacing to get that, and that's the power of this technique. And then very quickly, we looked at feed crawl that was lab made with this composition. I also have some results from a nickel chrome aluminum alloy, commercial alloy 214. We did it in air at the temperatures shown, and we did our form of thermal cycling for some of these, although I'm going to talk about isothermal results to start. And what you see here are these 2 theta scans that I showed you on a previous slide. And this is the type of thermal cycling experiment we would do. We would typically isothermally oxidize for a few hours and then drop the temperature sequentially, hold, and see how that changes the stress state in the scale as we drop the temperature. And you can very easily see that as we go from the high temperature where the slope here is positive, we go to the thermal stress from dropping the temperature by 400 degrees, and the slope is clearly in the opposite direction, indicating the compressive stress. And so we can easily distinguish between tensile and compressive stresses using this synchrotron radiation in fairly short times. Here's some early results where we showed the appearance of initial tensile stress for certain feed qualities and nickel aluminide. And I say certain feed qualities because, as you can see in the lab-made feed quality here, we saw a very early initial tensile stress that rapidly decreased with time. Whereas several other feed qualities, such as the Canthor AF alloy, showed essentially virtual no growth stress. I don't have a good reason for why certain ones show growth stress and not others, but it's clear that they different compositions had different responses, and we'll get back to that in a short while. For the feed quality alloy, we had the first observations of this initial tensile stress, but it has also been observed by others. And due to the work of Vio et al. At Oregon, again using synchrotron radiation, they not only saw this initial tensile stress, but they were able to extract a good mechanism for why it occurred. And it was from the conversion, as I spoke of earlier, of a Fe2O3 type of oxide to alpha alumina, which produces, by its displacements, a tensile stress in the oxide. And they very clearly showed this in this Nature Materials article. And I was happy to see that we weren't able to figure this out. We thought it, for some of our other alloys, maybe it was due to the conversion of theta on the nuclealuminide, but couldn't clearly see this as they did, where they showed the hematite decreasing with time as the alpha alumina peak increased. So regardless of this stress generation mechanism, stress relaxation appeared to be the dominant mechanism for the appearance of these curves as a function of temperature and time. And this is a busy slide, but here is the 1200 degrees C data that I showed you. You can see then at 1100, the tensile peak was even higher, but it also rapidly declined. At 1050, the peak occurred later and then started its decline. Whereas at 1000 degrees C, we never got to the point where it started decreasing with time. Again, we just went out to 4 hours. But if you think about this, it's a very clear an indication of some mechanism that's reducing the appearance of this stress during the earliest stages of oxidation. And again, I have to point out that because of the synchrotron radiation, we are able to get this data within 1 hour, whereas with a conventional X-ray source, you couldn't start taking data such as this until somewhere between 1 and 2 hours. So much of the action would have been missed using a conventional source. Now, Bull, earlier, several years before these measurements, Bull had presented a model of this competing stress generation and relaxation process. And his data, I repeat our data on the left for feed crawl, and his data for feed crawl is shown on the right. And even though the temperatures are off, they show qualitatively similar curves or behavior as a function of time. Again, his model takes into account both growth stress and then its relaxation by substrate creep. The model simply has a growth stress increment that's constant with time, and then it's being modified by creep of the substrate. And you get these similar type of curves indicating this dynamic interaction between generation and relaxation. However, as I already showed you, we do not have a growth stress that's constant with time. It decreases rapidly with time. And as I will show you over the next few slides, we believe our stress is not relaxed by substrate creep, but by creep in the oxide itself. And that's what I'm showing here. Using the analytical approach of Veal et al., we determined our stress relaxation rates using the Power law expression for creep. We used n = 2, but n = 1 would work fairly well also, as we know from the literature. But using n = 2 and doing the analysis, we determined at 1200 degrees C a relaxation rate at 100 megapascals of 2 × 10⁻⁷ inverse seconds, and an order of magnitude lower relaxing rates at 1100 C, as you can see here. So what do these to put these reaction rates in perspective? Both Veal and then us put these in terms of what are they from what we know in the literature. And on this plot, on the at the high temperature end, on the upper left-hand side, is data that Veal et al. Collected from the bulk alumina literature. And then in the lower right-hand corner is the results of Veal et al. For nickel aluminide. And you can see in many cases, their relaxation rates line up very well when you account for the temperature difference between the measurements. They found for nickel aluminides with reactive elements, the reaction rates dropped somewhat for nickel aluminide, but still followed the same type of behavior. And if you look at the range of relaxation rates based on microstructural differences, it's not too far off. They've also reported in the Nature Materials paper a relaxation rate that they measured in the same way that I measured them for feed crawl. And what they found is that it fell below this line, but again, it was in the vicinity of the other measurements. Now, the two measurements that we made for 1200 and 1100 degrees C are shown by these two red symbols, and you can see that it lines up very well with the data of FEO, given all the uncertainties of the analysis and the, for the nickel aluminide with reactive elements in it. So we're fairly confident that these relaxation rates are due to elastic deformation of the oxide. And the other reason we're pretty confident that these relaxation rates are indicative of the oxide is that we then took a specimen, oxidized it at 1200, measured the stress, and then we dropped the temperature to 800 degrees C, and we saw the appearance of this compressive stress, and we did a relaxation rate analysis on that, and we found 1 × 10⁻⁶, where we dropped 400 degrees in temperature, and yet the reaction rates went up. So we clearly have a higher rate of relaxation of the thermal stress than the growth stress, and we are pretty confident that this indicates, in this case, we have relaxation by creep of the metal, because creep rates, this kind of relaxation rate is on the order of what you would expect for creep at this temperature for these alloys. Okay, now I'm going to go to some work we did with thermal cycling, and this is the unpublished work that we've been working on and off for a number of years. We conducted stepwise thermal cycling with isothermal holes, as I mentioned before. We started at 1200, and we moved up to, we dropped the temperature to 800, and then we slowly then came back up in temperature to the original oxidation temperature, staying about anywhere from 20 minutes to an hour at each temperature hold. The reason we did this was to look at the creep hysteresis predictions of Hugh Evans and al., where by their definition, creep hysteresis is the interplay among stress generation and relaxation during thermal cycling. I'm running out of time, so I can't go into it in much detail, but what they found is that depending on the rate of cooling and then the rate of reheating, you could a tensile stress can emerge upon reheating, even when you had you had a zero stress state at the beginning of the test. And of course, the prediction was that creep in the alloy substrate, therefore, can lead to damage by this residual tensile stress in the oxide upon reheating. And they reinforced this model by their analytical and finite element modeling, but they also quoted a number of observations by a number of people in different systems based on gravimetric and a number of other experimental measurements. But there were very few, if any, direct measurements of these in-scale stresses at temperature after this thermal cycling. And this was our motivation for using our time at the some of our time at the synchrotron to look for these tensile stresses upon emerging from thermal cycling. And one of the predictions that Evans et al. Made was for creep hysteresis for alumina grown on Haynes 214. And this was this plot that motivated me to use some of our time at the synchrotron to look for these emerging tensile stresses. And we included Haynes 214 in the specimens that we tested, that we did experiments on at the synchrotron. And I want to show you those unpublished results now. But first, one of the good things about Haynes 214 and doing our experiment with it is that it showed very little growth stress. So we don't have a competition of starting with the tensile strength when we started the thermal cycling experiment. As you can see here, it's virtually very little stress at temperature at 1200 C. So we started the experiment by doing our 1200 C scan. We dropped it to 800 and then came up in 100-degree increments back to 1200. And you can easily see as we dropped it, we went to these high compressive stresses that were moderated or relaxed as we went back up in temperature. And it seems to think that it seemed to look like as we went got up to 1100, we saw a tensile stress, and indeed we did. As we show you on the next slide, we started at 1200 C, we dropped it to 800 C, significant compressive stress, which moderated or relaxed as we went up to higher temperatures. And then at 1100 C and 1200 C, we had this emergence of this tensile strength, the stress that wasn't there when we started, just in line with what was predicted by the Evans model. And then we did it again and then found another tensile stress. Now, if you look at these in some detail, it's not quite clear why the tensile strength is higher in the first case than in the other. But again, that's why the finite element modeling or modeling would be more important to help us understand that. And also know that these stresses are on the order of 100 megapascals. And so if you try to extract the tensile stress out of the residual stress at room temperature, when the compressive stress is on the order of 5 to 7 gigapascals, that's a very small number on a big number. And finally, we tried the same experiment for feed crawl. I don't have time to go into it, but we're not sure if we really saw the emergence of the tensile strength. We had some indications of tensile stress. We had some indications of that, but given the fact that it has a starting tensile stress, it complicated the picture very much so. So in summary, synchrotron radiation was used to directly examine stress development in alumina during the early stages of isothermal oxidation and during thermal cycling to intermediate temperatures. The results can be qualitatively understood and have to be understood in terms of the dynamic equilibrium of stress generation and relaxation as impacted by the temporal and spatial influences of oxide transformations and the microstructures associated with such. Both scale and substrate creep can play important roles in the relaxation of oxide growth stress. We made direct observations of the emergence of tensile stresses in scale after the thermal cycling to intermediate temperatures, and these are in agreement with the prediction of the creep hysteresis model of Evans et al. This model is an important one because it accounts for the net effect of the competing processes of compressive and tensile stress generation during thermal cycling and the associated relaxation that comes during the isothermal holds. This model indicates that stress relaxation in the alloy substrate is not always a benefit with respect to oxide integrity. And these at temperature diffraction results that I presented today really do support that conclusion as well as the model.